Hello, welcome to AB Video 4.2 and 3C Part 2, more on definite integrals and area. So, this time they're going to give you the integral and ask you for the picture again. So, instead of going from the picture to the integral, we're going from the integral to the picture. Sketch the region, i.e. shade, and sketch and shade the region, because it's a region, whose area is given by the definite integral. Now, the next interesting thing is they don't want you to integrate it by hand. They want you to use a geometric formula, and this is crucial, a geometric formula to evaluate the integral. Now, pathetic them couldn't come up with a number like -5 to 5 or -6 to 6. They had to just use -a to a and tell you a is positive. So the fact that you see an x here tells you that your left border is x equals -a, your right border is x equals a, your top border is f of x equals 4 or y equals 4, and of course your bottom border is the x-axis. So if you draw a left vertical line of x equals -a, a right vertical line of x equals a, and your top function is y equals 4, which is that blue horizontal line, and your bottom border is the x-axis, the region that's that's bordered by the two reds, the blue and the black, is this rectangle. And of course, the area of a rectangle is simply the length times the width. Well, from here to here is 2a, and from here to here obviously is 4, hence the area of that rectangle is 8a. Same thing. Now, over here, you might have said to yourself, yeah, but you know what, I could have done this by hand. I could have actually integrated 4dx and gotten 4x and then did the definite integral. And you're absolutely right, you could have. But you don't know how to integrate this, and you won't know how to integrate this by the end of this course or even by the end of the course next year. This is beyond the scope of AB or BC. But you can find this geometrically. So this is the same idea. The integral from -3 to 3 square root of 9 minus x squared dx. Right away you know everything's in terms of x. You can tell here, you can tell here. So that means this is x equals -3, which is your left border. Right border x equals 3. Top border is the function f of x equals the square root of 9 minus x squared. And the bottom border is the x-axis. When you take this f of x equals the square root of 9 minus x squared, if you square both sides and bring the x squared to the left, you'll notice it's a circle, center, origin, radius 3. But because it was f of x equals the square root, i.e. the positive square root of, it's only the top portion where the y's are positive. So it's a semicircle. Now, you can easily tell it's a semicircle. You can easily tell the radius is 3, and you can find the area of a semicircle by taking 1/2 pi r squared. So they could ask this question, and the sad part is they're not going to say use a geometric formula. They're going to let you sit there and think that you can actually algebraically integrate this, and you can't. Okay? So A, B, and BC don't have any clue how to do this. Okay? But geometrically, we get an exact answer. Okay, these are properties of definite integrals. I think they're going to be kind of self-explanatory now that you have a good idea of the first fundamental theorem of calculus and area. If the function is defined at x equals a, then the integral from a to a of f of x dx is 0. Well, no kidding, Sherlock. First of all, if you were doing a definite integral, whatever you integrate little f of x to get, whatever that function is, you're going to plug in a, you're going to plug in a, and you're going to subtract. Well, obviously, let's say the integral of little f of x is g of x. You'll get g of a minus g of a, which will give 0. So algebraically, it makes sense. Area-wise, you have a region bordered on the left by x equals a and bordered on the right by x equals a. Well, that's no region at all, is it? So that's why the area is 0. The next one, very important one, if f is integrable on the interval from a to b, then we define the integral from b to a of f of x dx to equal the negative the integral from a to b. Now, algebraically, if you think about it, let's say the integral of f is g of x. That'll be g of a minus g of b, minus g of b, and this would be negative g of b minus g of a. Well, negative g of b minus g of a is g of a minus g of b. So algebraically, we'll come back to what it means geometrically. Okay, additive interval property. So this is pretty simple. If you switch the order of the limits of integration, you have to stick a negative in front of it. That's algebraically, that's all you need to know. And here all you need to know is no matter what this function is, if the limits of integration are the same, the answer is 0, end of story. Here, if f is integrable on the 3 closed intervals determined by a, b, and c, then the integral from a to b of f of x dx is equal to the integral from a to c of the same function plus the integral from c to b. And we're going to show that that's true. Notice it doesn't say where c is. We're going to show that that's true if c is between a and b, if a is between c and b, or if a is less than c is less than b, or if b is less than c is less than a, etc. It doesn't matter where c is. Okay, these other two properties are extremely simple. Basically, what this is telling you is the old formula you knew from before. If you have a constant times a function, you can pull that constant on the outside. It's saying that you can do that with definite integrals. And just like before, we could break up an indefinite integral of the sum of, or difference of two functions and break it up. We can do the same thing with definite integrals. You just got to keep those limits of integration the same. Okay, and then the last one is if f is integrable and non-negative, in other words, above the x-axis or on the x-axis on the closed interval from a to b, then you're going to get a positive area. Okay, kind of we already knew that. And obviously here, which we'll see later, if they're both bordered on the left and the right by the same thing, if f of x is lower than g of x, then the area bounded by f of x and the x-axis is going to be smaller than the area bounded by g of x. Okay, so again, looking at these, if that's the same, there's no region at all. If you look at it algebraically, it'll give big F of A minus big F of A. Over here, so now let's look at it. This is looking at it algebraically. This would be if the integral little f is big F, then this will be big F of B minus big F of A, and this will be negative big F of A minus big F of B, which is the same thing. But I want you to understand this geometrically. If you're going from A to B, your dx's, you're going to be adding a number each time to get from the left to the next one to the right. Meaning you're moving to the right, so your dx's will be positive. On the other hand, if you're moving to the left, if you're going from B to A, then obviously your dx's are going to be negative because you'd have to subtract to get to the next thing. And that's another reason why what happens here is if you are going from B to A, let's pretend f of x is above the x-axis. If you're going from B to A, then your dx's will all be negative, which means, and your f of x's will still be positive because you're still above the x-axis. But this expression will be negative what you expect it to be as far as area. Multiplying it by a -1 is going to force it to become the positive